Well, I'll say good morning to everyone. So there's a lot of old homework up here I'm trying to get rid of. I hate carrying it back and forth every class. And the exams have been graded, and I'll hand them out at the end of the class. I learned years ago you shouldn't hand them out at the beginning of class, because teaching a class when you have a hostile class is never good. So always wait until the end of class to hand them out. So last class we were talking about testing the corner cubes, and first off we said, well, a corner cube you get when you have 6 different reflections coming back. If you look at, you have 3 surfaces, and you look at the different combinations of orders in which the light can reflect off the 6 surfaces, you end up with 6 combinations. And so you have 6 interferograms. Now, if the corner cube is perfect, the surfaces are flat, angles are 90 degrees, what's the shape of the fringes you get? Straight, equally spaced. And we, in the single pass test, we can change the number of fringes simply by tipping and tilting the reference surface here. And so we would get the straight, equally spaced fringes, as we said. And if the angles are not 90 degrees, but the surfaces are still plane surfaces, we'll get straight fringes, but they will go at different angles in the different 6 different regions here. And this would be for adjusting the flat so the beam is retroreflected here. And if we tip and tilt this, we'll change this pattern a little bit. But we can still determine just what the errors are, independent of how we tip and tilt this, simply by looking at the tilt difference, as we defined tilt difference last class, between any 2, between consecutive interferograms. And so if I look at the tilt difference between here, this would give us the error in one of the 90-degree angles. And it turns out that the error is a tilt difference divided by 3.266 times the refractive index. And I gave you this reference here where a former student of mine, Dave Thomas, went through and derived this expression here. And it's up on my website. Now this is it's a good test, except there are a couple of problems, as we said last class. One is we're getting essentially 100% of the light reflected back here. And we're getting probably 4% from this surface here. So the fringe contrast would not be very good, but we could put an attenuator in here and match the intensities of the 2 beams and still get good fringe contrast, so that's not a problem. But the bigger problem is that the beam reflecting off the corner cube is flipped over, kind of a strange way. All these various 6 beams are flipped over. And the beam reflected from the reference surface is not flipped over. And so errors in this collimated beam do not cancel. And as we have said many times, if you just go out and buy a commercial Fizeau interferometer, this beam probably has, I don't know, a fringe or 2 fringe errors in it or so. I mean, it could be made better, but the commercial ones just aren't, because normally you don't need a high quality beam here. As we've said before, normally the errors will cancel, be in both beams, but this is one case where they don't cancel. And so this is the single pass test of the corner cube, just like the single pass test of the 90-degree prism. It's not very, very good. And so what you do is the double pass, just like we did for the 90-degree prism. So first off, we need an interferometer where we can stick a beam block in here. And most commercial interferometers will have a space between the box holding the laser, the camera, and beam splitter, and all kinds of things, and the reference surface, which is generally called a transmission flat. So you stick in a beam, stick in a card here to block half the beam. And now what we're going to get is, well, I'm going to claim, we'll go back and think about this for a second. I'm going to claim that if the corner cube is perfect, we're going to get one fringe here. And I'm going to claim that even tipping and tilting the reference surface is not going to change that one fringe. If we have errors in the 90-degree angles, then we'll get something like this. And tipping and tilting the reference surface will not change this pattern at all. Now let's see, does that make sense here? So it's sort of the same way that we were talking about for the 90-degree prism, except the 90-degree prism just worked in the plane of the screen here, while for the corner cube it works in the plane of the screen and out of the plane of the screen. So what we have then is one beam reflected from here, and the other one goes through here, reflects here, and comes back. And if this was perfect 90 degrees, the beam would come back in exactly the opposite direction it went in. And it will reflect off of this surface and come back here, reflect here and out. So first off, we got 4% from here, roughly, and we're getting almost 100% here and 4% there. So we have automatically matching the intensities of the two beams. So that's great. But in addition to that, what is happening here, if we think here for a second, let's, just like we did with a 90-degree prism, let's think here again that let's tilt this clockwise. And so this beam would come in here, would come back there, would come up at an angle. If this is tilted clockwise, the beam would go up here. This beam will go through here, through here. Now if this is tilted clockwise, this beam will come here and will come down there. So it's coming down, and so when it leaves the corner cube, remember it's going to go in the opposite direction, so it's going to go up. And so it's going to go, tilting this will cause the reference beam to go up, and it's also going to cause the test beam to go up. Are you convinced of that, or am I trying to pull something over on you? So I think, tilting this is it's going to do the same to both beams. So how do I introduce tilt fringes in this pattern? How would you introduce tilt? I might give you an extra 5 points on your test if you can tell me how they introduce tilt, because I don't know how. Well, what people used to do, I mean, what they used to do, I mean, tipping and tilting this doesn't change the tilt at all. I mean, it changes both beams, and so you can't introduce tilt fringes. Kind of weird. What? Ah, very good. Oh, do I have to give you 5 more points here? Well, it's not in the reference, in the test. You put it in the test. You put a little, you put a little prism right here, and then that will introduce tilt. Very good. But I mean, if we're doing phase shifting, who cares? We don't want the tilt. And so, I mean, this test, be truthful, there were papers that talked about putting prisms in here and stuff. But before phase shifting came along, this was not used, just because they couldn't easily change the tilt. And but when phase shifting came along, well, who cares? I don't need to introduce tilt with phase shifting, so it would work fine. Even if I, had a really nice corner cube, so the fringes maybe a 1 fringe or close to 1 fringe, I can still measure it. It's fine. Now there is one other tricky thing I just thought of here. I used to remember it when we used to sell these instruments. That the most common, go back here. Normally, phase shifting interferometer, how would you do phase shifting in this interferometer? Typically, the most common way, you would move the reference surface. You would move the transmission flat. Normally in these interferometers, This is mounted on a PZT. And if I want to do phase shifting, I would apply a voltage at that PZT, and that would move the reference surface. And so that would change the path difference between these two beams. Okay? And most of the Fizeau interferometers sold, that's how they work. Mounting the transmission flat on PZTs and then moving this. And if I want to change the phase shift by 90 degrees, how far would I want to move this transmission flat? Lambda, so I want the OPD to change by lambda over 4. And so I would move the reference, the transmission flat, how far? Half of that, lambda over 8. Okay? So if I move this 1/8 of a wave, this path length will change by twice that, or a quarter wave, and I'll get my 90-degree phase shift. Okay? So I want to move it by 1/8 of a wave to get a quarter wave phase shift. How far do I want to move this to get a 90-degree phase shift? So I still want to change the OPD by a quarter of a wavelength. If I move this a small distance, I will change the reference beam by twice that distance. This beam comes around here, here, and here. Ooh, I'm also, if I move this to the left, I'm making this longer by the same distance. So if I were to move this 1/8 of a wave, I would change this by a quarter wave. I'd make it shorter by a quarter wave, and I would make this one longer by a quarter wave. And so I no longer want to move this 1/8 of a wave. I want to move it a 1/16 of a wave. So if you're selling these interferometers, you have to some way make it so when you tell the computer you're testing in a corner cube, it changes the voltage going to the PZT, because you now want to move this half as far as you normally would. Okay. So we get, this if it's perfect, or if we have errors in the angles, then we're going to get, we're going to get 3 interferograms, and the fringes are going to be at different angles in the 3 interferograms. And tipping and tilting the reference will not change anything. And what I can do now, if you go through, well, I've double passed, so I actually am picking up twice the error that I did back here, but I'm looking only at 1 interferogram. And so what I do now is just look at the tilt in each one of these interferograms, and again the error is given by the tilt in that interferogram divided by 3.266n. Errors in the collimated beam have canceled out. I've matched the intensities of the 2 beams very well, and this is an excellent way of testing corner cubes, and it's widely used, and it's probably, well, it's good to a sub-arc second, very, very small errors. Yes?
Did you ever care about other errors like power?
Yeah, okay, well, good question. What if, what if the surfaces are not flat? Maybe a little curvature or something. What will I see here? Well, I'm not going to see straight fringes anymore. It's going to be curved, yeah. And so now, well, now really the problem is the angle between the different surfaces is not unique. It depends on where you're looking on the 2 surfaces. And so you can sort of get an average angle or something, or you can just measure you can determine what the wavefront is, and sometimes that's of interest. But I have to admit, in practice, I've almost never seen fringes as nice as straight as this in a real interferogram from the corner cube, because the surfaces always are, well, they're not perfectly flat. So these fringes are always a little curved. Okay, any other questions? Well, the other problem, or potential problem, is that these reflections inside here can change the state of polarization. And I've even read in the literature that sometimes you can't even see the fringes because the polarization is so messed up that the fringe contrast goes to 0. I've never experienced that, and I've looked at lots and lots of corner cubes. But you can see that the fringe contrast may be reduced a little bit because of changes in the polarization of this beam, getting elliptical polarization out. But I've always been able to get good enough fringe contrast that you can measure it. Any other questions on the corner cube? I love the corner cube. I love looking in a corner cube. I think back when I took the prelims at Rochester a long, long time ago, in the room where I took prelims, for some reason they had this big corner cube. So I'd be working away on my prelims, and every time I'd look up, what would I see? I'd see my eye staring right back at me. So I remember that. Maybe that's why I like corner cubes. I don't know. Okay, so we've talked about mirrors and prisms and both the surface quality of prisms, prisms and transmission, angles of prisms. What I want to do now is talk a little bit about measuring diffraction gratings. So, and I'm thinking in particular a diffraction grating that has straight lines in it, straight equally spaced lines in it. And what I want to do is to measure the straightness of these lines and the spacing variations of the lines making up the diffraction grating. Now, I guess I've been in this business long enough that everything I look at, anything with any straight lines, I think of, oh, it's an interferogram. And so when I think about a diffraction grating and look at all these lines, I think, oh, that's sort of like an interferogram. Well, that's sort of, an interferogram and a hologram, well, they're the same thing. So a diffraction grating is sort of like a hologram. And I just want to go through a little bit, a few lines of algebra here to show that you can really think of the diffraction grating as a hologram. And I really don't need the algebra. You just see it and you know it's a hologram. But let's go through it anyway. So let's say I had a perfectly straight line grating. And let's say the line spacing is delta x. And the lines, and I could just write as x over delta x is m. So as I go from one line to the next line, m is an integer. And as I go from one line to the next line, m will change by 1. So this is just an equation of a straight line representing my grating lines here. Now, that's if the lines are perfectly straight and equally spaced. But let's say the lines are not perfectly straight and equally spaced. Let's say there's some errors in these lines. And let's say the error in the line position is some little delta, which is a function of position xy. That's the error in my line position. And so I could write an equation here describing these lines as x plus delta as a function of xy divided by delta x. So that would be an equation describing the lines that are no longer straight. Okay. Then I could say, well, if I had a tilted plane wave, I could just write that as e to the minus ikx sine theta. So k being 2 pi over the wavelength. Theta represents the angle of the tilt of this tilted plane wave. And if I had a beam that had some aberration delta w of x and y, then I could write that wavefront, and say it's unit amplitude, both these are unit amplitude, I could write that wavefront as just e to the ik against 2 pi over lambda, e to the ik delta w of x and y, where delta w represents the OPD of the aberration. And if I were to interfere these two beams, so I would add these two and multiply by the complex conjugate, something you've done a million times, you end up with something that goes as 1 plus a cosine of the phase difference between the two beams. And so I just take the difference between these two. One of these I picked positive, and the other one I picked a negative here. And so the difference would be kx sine theta, which represents the tilt, and a k delta w, which represents the aberration. And for a bright fringe, I could say, well, if this is m times 2 pi, then the cosine would be a +1, and that would be a bright fringe. And so I can take the kx sine theta plus k delta w of x and y and set that equal to 2 pi times m. And I end up then for a bright fringe, x sine theta over lambda plus delta w of x and y over lambda is equal to m. Okay. So lo and behold, that sort of looks like the equation I had here. And therefore, I can say for a grating, if I illuminate the grating with a plane wave, I'm going to get different orders coming out of it. If this is a perfect grating, then all the different orders would just be plane waves. But if I have errors in this grating, then the aberration in the first order, in units of waves, is simply delta, the error in the position of the line, over delta x, which was the average line spacing. And if we go back here, I didn't even need to do this equation, but I just thought about this for a second. We've looked at interferograms, and we said, if you have wiggles in the interferograms, well, the error, it's like interfering a plane wave with another beam where the error in this other beam is simply given by the deviation from straightness of the fringes divided by the average fringe spacing. And so that's all this is saying here. So it's just another way of saying, this grating is like an interferogram. And if I illuminate the grating with a plane wave, then I'm going to get a beam in the first order of delta over, little delta of xy, the error in the positioning of the lines, divided by the average spacing of the lines in units of waves. And if you go to the nth order, this may not be quite so clear, but if you go to the nth order, you'll have n times as much aberration. So if this is the aberration I have in the +1 order, the -1 order turns out to have minus this aberration. The second order has twice this aberration. And you can just get that by writing that out in a Fourier series and see that's the case. So if I take a grating here, so this is my grating, and it has some errors in it. And if I illuminate this with two beams, well, let's first just illuminate with beam number 1. I will get a diffraction order here, and let's say that's the nth order. And if I illuminate with another beam here, I'll get, again, many orders, but I'll get one order coming out here, which will be the -nth order. And these two beams can interfere then, and I've used a spatial filter here to get rid of all the other beams. And so this will interfere to have 2n as much aberration in it as what the first order would have, or 2n the sensitivity. So let's say I have a number here. I have 200 microns per fringe. If I have 200 microns per fringe, and let's say I had a 2 micron error in the location of a fringe, then the first order would have 100th of a wave error in aberration. The nth order would have n times 100th of a wave error in the aberration. And here I have 2 plus n and minus n, so I'm actually having a sensitivity of 2n times 100th of a wave aberration. So is this fuzzy or is this clear? Because this turns out to be a pretty good way of testing diffraction gratings, straight line diffraction gratings anyway. Fuzzy or clear? What? A little fuzzy. Okay, I thought maybe it was. But, so where are we fuzzy here? Are we fuzzy down to this point here? Don't understand what?
How do you get the n times as much average?
Yeah, well, think of, I have a little displacement here. Maybe I can draw this. So I'll just say I have one. And so I have some fractional, this is some fraction of a fringe here. So I call this what, delta x. And this little bit here is delta of x and y. So we can see that that's some fraction of a fringe. Are we okay at this point? Well, if I look at the second order would be like these lines would be twice, would be half the spacing, twice the frequency. And so for a second order, I'm looking at double the frequency, so it's supposed to be the same thing there, now one here. So this now, the fraction of how much off that line is from the double frequency, second order, is twice as large. I could expand it out in a Fourier series, but I think it's maybe just easier to see it this way. Or, remember that the sign of this, whether it's a hill or a valley, depends on the direction of the tilt. And so a minus order would be minus the direction of the tilt, so the sign of that error would change relative, plus order to minus order. So how large that error is compared to the period that we're looking at increases as the order number increases. If I go to third order, then that would, the lines are 3 times the spatial frequency, but this error is still the same size, and so the fractional fringe would be 3 times as large. Yes?
So is that defect, is that due to the surface of the brush tree, or like it didn't perfect?
No, when they drew the lines, however they made the lines aren't straight. The lines have a little wiggle in them. So
You should have had like discontinuities that was.
this was a weird thing here. This was drawn by some computer plotter, and every now and then, as it was drawing the lines, it would just jump over. And so we really had discontinuities here. And if you looked at this under a microscope, you could see that these lines actually jumped. Just some error in this. It was a laser beam recorder, an old one. I kept this figure because I always liked it, but people who made the laser beam recorder didn't like my figure very much. So you could change the sensitivity of this test here by changing the orders that you had interfering. And you could interfere, no, you could interfere a 0 order from one beam with a +1 order from the other. I typically would, so these are, I typically would interfere +n with -n because they would have the same intensities. If I interfered a second order with a third order, they probably would have different intensities. Or second order with minus third order. Okay. Is it still fuzzy? Less fuzzy. What?
Less.
Less. Good. Good. I mean, this is nice. I mean, you could look at these gratings under a microscope and maybe do some measurements. Here you're getting the whole grating all at once. And I think you just analyze it like you would a regular interferogram. And you could quite nicely determine just how much errors you had in the lines. Now, if I drew something other than straight lines, maybe I drew a zone plate, then I would expect to get a spherical beam. If I illuminate with a plane wave, I get a spherical beam coming out. And so I'd want to interfere that with another spherical beam. You want whatever it is you're interfering to be about the same shape. Shall we go on? Yes.
Are you using the diffraction grating itself to generate those two orders, and then you're retroreflecting back through it again?
Well, okay, maybe this isn't clear what I have. So here's my grating. And some way I'm producing two beams of light. I have some other optics over here producing two plane waves. And so I'm just illuminating this. Let's say I illuminate it with one plane wave. I get a beam coming out here. And I'm getting, several orders. So I'll put in a small aperture here to select one order. And so I just say, well, that's order plus n. And then I have another plane wave that I'm illuminating this with. And then I'm adjusting this angle. If I change the angle of this beam, the angle of the order will change too. And so I'm adjusting this right here to be so that these two beams, the plus n order from beam 1 and minus n order from beam 2 come out here at the same angle. And if I were to tip and tilt either one of these beams, then I would change the number of tilt fringes here. So let's say I have a grating here with some line spacing. Let's just call it delta x. And if I wanted to interfere the 0 order with the +1 order, what angle would I have between these two beams? Well, these two beams coming in here, you could think of them as producing a fringe pattern. And if I want to interfere the 0 order from one beam with a +1 order from the other beam, what would the spatial frequency of this fringe pattern be relative to the line spacing of this grating? It would be the same, it turns out. And so in this case, where I'm interfering the +n order with -n order, how large is the spatial frequency of the fringes I produce by interfering these two beams with the line spacing of the grating? The answer is going to be 2n. 2n is large. So let's go back here to where I adjust these angles here. So I'm interfering the +1 order from one beam with a 0 order from the other beam. And I'm saying, well, the spatial frequency of the fringes is equal to the line spacing or spatial frequency of the grating. And so you can think of this, I mean, moire. I think whenever, I'm illuminating something with, I'm illuminating this grating with this fringe pattern, and I'm really seeing the moire of the two. And I'm doing some special filtering here so I don't see the high frequency stuff in the moire. So this is sort of like a higher order moire here, where I have two n times the frequency of the grating here. And that's what I'm seeing here, spatially filtered. Sort of back to the exam question. Some of you were very good on this question, and some of you were terrible on this question. So what I'm doing here, the moire pattern, I'm always seeing the difference. So I'm seeing the difference between the fringes formed by interfering these two beams with this pattern here. And like the homework problem where I had one equation describing one pattern and the other equation describing the other pattern, I'm seeing the difference. So the whole answer was to subtract the two equations, not multiply them, not add them, but subtract them. And about half of you were very good at that, and half you, it was sort of a binary. You got 5 points or you got 0 points, the way it worked. Okay. So anyway, I think this is kind of cool here, kind of neat the way it works. So any more questions on it? Okay, one more topic in this section, and I never knew if this is the chapter it should go in or not, but I had to put it someplace, so I put it here. So what we're doing now, we're going to make some optics. We're going to make a lens, we're going to make a prism or something, and I have a big chunk of glass here that we're going to make this prism out of, say. And the question is this a good, is the glass good? Does the glass have any index variations in it? Or is it uniform? And so how can I determine that? Well, I guess, if I really were ambitious, I could take this chunk of glass and I could polish the two surfaces real flat, and I could test it as a window. So, you could test each surface as a mirror, and then you test the whole thing as a window, which we all know how to do now. And if a surface is a flat and I test it as a window and I see any errors in it, that's due to the index variations in the sample. So that would work. So why don't I do that? I just get a piece of glass, I flatten the two surfaces. Maybe I want to make a lens out of it later, but right now I'm just going to flatten the two surfaces, put real good surfaces on it, test it as a window, and determine if I have any index variations.
Because it's expensive to make flats.
Oh yeah, it's too much work. I'm lazy. I don't want to. You're going to make these flat surfaces. You're going to make very good quality flat surfaces, but you don't want a window. You want to eventually make it into a lens. So you've done all this work and it just, doesn't make sense. So forget that. We're not going to do that. So the next approach, and this is the approach that has been used a lot over the years, and is that you buy or you make two high quality flat windows. Okay? And I'm going to use these over and over and over again. So I don't mind spending, I never like spending a lot of money, but I'm willing to spend a lot of money to get these two flat windows. Now I'm going to put my sample in here. Now the sample doesn't even have, surfaces don't have to be flat. It doesn't even have to be polished. It can be ground. And what I'm going to do is to put an index matching fluid that matches the index of the sample, sort of the average index of the sample, in between these flat windows and the sample. So the windows are flat on both sides. put this index matching fluid in here. And so this is index matching out any height variations on the surface here of the sample. And now I'm going to test the whole thing in transmission, like a window. And I know these windows here, these are good. I know that from previous using them before. And I match, index fluid, match out any height variations here. And so now anything I measure in transmission, well, I know really corresponds to index variations in this sample here. And so I've gotten rid of having to work on every single sample that I'm testing. And so this is a better approach. And this is widely used. I remember years ago I was visiting Schott in Germany, and I saw the room where they tested hundreds or thousands of samples this way. And I've done this myself many times. But I have to tell you, every time I've done this, I've ended up with this oil all over me. Just a mess. The other thing is this index matching fluid has to match the index of this material here. And it seems like you can always find that fluid in some way, but it might be poisonous. So that's why I'd always have the graduate students do this for me. So, it's dangerous. Plus, being a cheap guy, I didn't like having to spend money for these windows here, although I could use them over and over again. But anyway, you could do this, but and it's used a lot. Even today, it's still used. But it does require you're working with some strange materials, index matching fluids. It does require you to have flat windows, and if this is a real large flat, these flat windows have to be very large. So is there a better way of doing this? And the answer is yes. And once upon a time, I thought I had invented this answer, only to find out it had been invented before I was even born. It's been around a long time, this approach we're going to go through. But it really was not real useful, until phase shifting came along. Because what we're going to have to do here, what we're going to do is that we're going to be able to measure this sample, that the surfaces have to be polished, but they don't have to be flat. They can have all kinds of errors. That's okay. And even in my interferometer, the transmission flat, the reference surface doesn't have to be good. And the return flat doesn't have to be good. We're going to go through here and we're going to do 4 measurements, and we're going to subtract out all these errors, and we're going to be left with just errors due to index variations in this sample. And I love this, because this is an example where we're going to do measurements that are better than the reference surfaces. Reference surfaces don't have to be good. Interferometer doesn't have to be very good. But it does require 4 measurements. So what I said was, this technique has been around a long, long time, and I tried to figure out who actually invented it. And it goes back so far. It's hard. I was never able to figure out who the first person was to invent this. But it requires 4 measurements, and in order to have good results at the end, all 4 of these measurements have to be very accurate. And so that's where phase shifting came along. Before the days of phase shifting, you couldn't really make these measurements accurately enough such that when you get done, you still had accurate results. Okay, so what are the 4 measurements here? So, well, first off, let's say that on this transmission flat, we have errors that I'll just represent as A. And they're all over the surface, not just one spot here, but errors of A. On this glass sample, we have errors of B all over the surface. On the second surface, we have errors of C. And on the return flat, even that's not very good. It has errors of D. Okay, so the first thing I'm going to do is that I'm going to look at the interferogram formed by light reflected off this reference surface here and the first surface of the glass sample. So light reflected from the front surface of the sample and the reference. And what I'm measuring then will be twice the errors represented from A and twice the errors represented from B, because it's, back and forth. Okay? So that's my first measurement. So I do that measurement, store that data in the computer. The second measurement is I'm going to measure light reflected through the sample and reflected off the second surface. So again, light reflected from here, light going through the sample and reflected off the second surface. So what I'm measuring then is, again, I have the 2b minus a. Then I have n naught is the average refractive index of the glass sample here. So I'm measuring 2 n naught c minus b. C minus b. Plus, if I have any index variations in the sample, I'm going to go through the sample twice, and so I'm going to measure some OPD due to the index variations in the sample. My whole goal is to determine delta, then, the errors due to the index variations in the sample. So that's my second measurement. Oops. Now this is a little bit of a problem here, because I'm measuring through the sample and reflecting off a second surface, and I don't want the reflection from the first surface to mess me up. And so the normal restriction here to this measurement technique is I have to have enough wedge in this sample so I can pick a reflection from the first surface or a reflection from the second surface. But I don't get both at the same time. So that's a restriction. We have to have a little wedge in here. I mean, that's the normal restriction. But those of you who have taken this course know you don't really have to do that. If I have, remember when we talked about this low coherence length interferometer, where in the source part of the beam, I had a beam splitter and stuff, and I got two beams coming out with a time delay between them, and I could vary what the time delay or path delay was. And so if I go back and use that interferometer here, the short coherence length interferometer, I no longer have to have wedge here. But without that, I'm going to have wedge. Okay, that was my second measurement. The third measurement is I'm going to go through the sample and reflect off the return mirror. So third measurement, I look at the reflection here, I go through the sample, and I get a reflection there. And I measure that. So that, again, I have a 2b minus a. I have a 2n naught c minus b. I still have the 2 delta, but now I have a d minus c here to worry about. So this is the mess I'm measuring with a third sample, a third measurement. The fourth measurement here is I'm going to just take the sample out, remove the sample, look at the reflection from here and reflection from there, and what I'm measuring then is 2d minus a. So I have these 4 measurements here. Now, so I know all the OPDs, point by point, across the sample. I know what n naught is. I know what the average refractive index is. I don't know what delta is, and I want to determine delta. And I'm going to just write down the result here, but I'm sure all of you will go back to your office and go through the algebra just to make sure I'm not cheating here. And the result that I can solve for delta here, it turns out if I take this third measurement minus the fourth, and I multiply that by the average refractive index of the sample, I take the second minus the first, I multiply that by n naught minus 1, and I subtract these two, and I divide the result by 2, I get delta. And delta is the delta n, the variation in the index of this sample, times the thickness of the sample. So it's really the OPD due to the index variations in a sample. And all these errors in the transmission flat, in the return flat, and on these two surfaces here, all these errors go away. And I'm simply left measuring index variations here. So the only work I had to do on this glass sample was, well, to put a shine on it. It had to be polished enough so I could look at the light reflected off of it and get light transmitted through it. But the surfaces didn't have to be flat at all. So I don't do much work on it. And I can measure the index variations. So isn't that cool?
So is that the index variations in a single value, or is that?
That's I should write that as a function of xy. So I'm doing this over the whole sample here. So I'm doing, I'm measuring the whole sample. So this is really a function of xy. And here's a result of a, this was a terrible sample. And I published it at one point, and the person who supplied the sample to me wasn't very happy about it. But I didn't put their name associated with it, so it's okay. I thought it was okay anyway. But anyway, this is in looking at lines of constant OPD for this lousy sample.
That's only due to the glass?
That's only due to the glass, not due to the surfaces. All the surface errors dropped out. This was the best sample I ever tested, which means it was the worst sample I ever tested, but it gave the prettiest results, I thought. So this is actually quite a good technique, and back in my WICO days, we put this in a software and sold quite a number of interferometers for doing this type of testing. And as I said, I thought I had invented it at one point, but it ended up that it was invented long, long, long ago. But it wasn't popular until phase shifting came along, because each one of these measurements has to be, rather accurate in order to get something at the end that's accurate. And so that's where, with phase shifting, you can do good measurements here. And the other thing is, back in the WICO days, we always had to have the wedge in here because we didn't have an interferometer with a short coherence length. But by going to that interferometer that I showed you earlier with a short coherence length, you no longer have to have wedge in that sample, because you can pick which side you're looking at. Any questions on that? Okay, well, always thought that was pretty neat. Well, that's the end of chapter 7. So I'm actually ahead of schedule. That's not supposed to be finished up until Thursday of this week, but I'm sure we'll find plenty to talk about here. So that was on flat surfaces, if we go back to the beginning here, just to remind ourselves. So what do you think chapter 8 might be on? Curved surface. What a good idea. Let's do that. Okay, chapter 8. Yeah.
Going back to the index measurement, would your n and n naught for the difference be like different values in the next slide?
Oh, what might be 0.00.
On the next slide you had like, okay, everything's equal to your difference.
Yeah, so this is the index of what the material is supposed to be, kind of the average index. Right here?
Yeah.
So this is the index as a function of position.
Okay.
And so I'm measuring. Now, I mean, this right here, this line right here is fine. The little assumption in getting down here. So this is the index, this is the OPD due to the index variations. Now this would be true here only if we had this index across the whole T, across the whole thickness. And you may have that, or you may just have little region, maybe only in the center of the glass is the index high. So it's for sure we're measuring index variations due to, we're measuring OPDs due to index variations. And if I can assume that the index is across the whole thickness, then I can write this last equation here. Any other? Yes? T is the average thickness, yeah, right. So if I had a wedge, of course, T is varying. But, and, you know, the surfaces aren't flat, T is varying a little bit. But, I mean, it's varying microns probably, and the thickness is centimeters. So this is just sort of the average thickness. So as I said, this next to the last line, this is true, and here it's a little making some assumptions for the very last line. This is generally what you want here is the delta anyway. Okay, anything else? Okay, curved surfaces. Well, this is going to be a long chapter, and this is actually a fun chapter. Of course, the last chapter was a fun chapter too, and chapter 9 is also going to be a fun chapter. But anyway, what we're talking about here is first, we'll talk a little bit about, we want to measure what the radius of curvature is. And we'll say a little bit about spherometer, autostigmatic measurement, and Newton's rings. And then we're going to go on and talk about measurement of surface figure. So how does the surface depart from a sphere? And we've already, the first three things we've already talked about. Test plate, I'll just say a couple words. Twyman Green, loopy, you're experts on that. And so I won't say much there. And Fizeau, we won't say much. But I think they have to be included here because they're important things for measurement of surface figure. Then we go to the SWIM interferometer, which you have not seen before. It's not a real useful interferometer, but there's a couple of points there that are very important that I want to make. Then, well, Shack cube interferometer. So who invented the Shack cube interferometer? Who do you think? Roland Shack, right? And that's, as I probably have told you before, when I retired as dean, I looked around and said, whose office do I want? And Roland Shack, who had retired, Roland was so smart. I thought, I'm going to take Roland's office. Maybe some of his brain cells are still in there, but I haven't found him yet, but keep looking. Oh, then a scatter plate. I love the scatter plate. We're going to talk about the scatter plate. I've had 2 students do their PhD on the scatter plate interferometer, and this is an absolutely amazing device. It shouldn't work, but it works extremely well. And then we'll talk about the smart point diffraction interferometer. We'll talk about the Summergren diffraction interferometer. I have to say a few words about measurements of cylinders. Talk about long wavelength interferometry, star test, and again the great name Shack-Hartman test, Foucault knife edge test, wire test, Ronchi test, 1,000,001 lateral shear interferometers, and radial shear interferometers. So we have a lot of different measurements, a lot of different ways of performing measurements of curved surfaces that we'll talk about. So this is going to be, it'll be a lot of fun here. And we also, I didn't mention, but curved surfaces including lenses. Okay, I spend a little bit of time here before I hand out the exam talking about the measurement of radius of curvature. And there are 3 techniques that we're going to talk about here: a spherometer, autostigmatic, and Newton's rings. So we'll first go to the spherometer. And I love this picture here. I wish I could remember where I found that up on the web. But whenever I look at this, I think of John Grievenkamp, and I think he would love to have one of these in his antique optics collection here. Maybe he does have one, but I haven't seen it. So this is an antique spherometer here, but it shows you basically what you do. You put something on. You're going to measure the sag of this spherical surface, and from the sag you're going to calculate what the radius of curvature is. And so for this old thing here, you have 3 points. That scares me, setting something down here with just 3 sharp points, but we'll do it for right now. Have 3 points here, and we know the spacing of these 3 rods. And we have this little thing that we can turn the knob here and move this center point up and down. And when it touches the surface here, we'll read off what height is at, and that will give us the sag. And from the sag, we will determine the radius of curvature. Now, spherometers are widely used. Have any of you probably have used spherometers in lab, yeah. And you probably, when you used them in lab, did you have sharp points here or did you have little balls? Yeah, balls are better. Sharp points on optics, not wise. But anyway, you generally have 3 small balls here, and they're arranged in a triangle here. And at the center here, you have some probe. And I don't know if you used one where you read off a micrometer, or nowadays, most of these are, the new ones anyway, are electronic digital readout. And so you don't even have to do any work. You just read off what the digital display says. And so let's look a little bit here about calculating the curvature from the sag. And if the sag of the surface is h, and let's say that the distance between the centers of the balls is d, and now if it's not just a sharp point, but it's a ball like you normally have, then the radii of the balls, we'll have to know what that is, and that's r. And then it turns out, and we'll derive this expression in a second here, turns out the radius of curvature of the unknown surface is given by d squared over 6h plus h over 2 plus or minus r, where the sign here, plus or minus, depends on whether the surface is concave or convex. And if it's concave, I guess the sign that we use is plus. And if it's convex, then we use the negative sign here. So I want to derive that, and looking at the time here, I think I'll wait till the next class to derive it, because I want to hand out the homework here. Make sure we have time to do that. So we'll come back at the beginning of next class here and go through a short derivation for this equation here. So you can end recording here, and